All right, problem 29 in group theory. Prove that index is multiplicative if H is a subgroup of a group G of finite index and K is a subgroup of H of finite index, then the index of K in G is equal to the product of the index of H in G times the product of the index of K in H. Okay, so we're going to start with our assumptions. Suppose that H is a subgroup of G of finite index, and K is a subgroup of H of finite index. So we have something to work with. We're going to let, I'm going to switch notation to just the bars, but the index of H in G equal M, and the index of H and K and H, it's backwards to what I say, equal M. Yeah, let's see. The product of that is N times M, sure. So we're going to use a characterization of index, which is that we can choose representatives for left cosets. So we can write G as the cup, okay, slash big SQ cup, start at I equals 1, go to N for GI, and we have H. So this is, we can choose representatives for left cosets. So this is a categorization, and we can quad, and we can also write H similarly. So maybe I'll format it like this. H as also the disjoint union from J equals 1 to M of, we'll do Hj of times K. Okay, and we'll add another quad just to format this a little better. Okay, and we can do this since we have finite index. We can write them as disjoint unions of these representatives Gi and Hj times their respective respective subgroup. Okay. Now we can take this first guy and, well, we can take the second guy, the H equals, and substitute that back into the first H. So substituting, let's spell that correctly, substituting H into the first equation gives, all right, we have G equals, and let's just do some copying and pasting. Let's take this guy, but instead of using H, we'll just use whatever H equals, which is this guy. Maybe we'll put it in parentheses like that, but, oh, copied the wrong one. We want H. Oh, I thought I switched this to an M, but maybe I didn't. We'll switch that to an M, switch that to a J, and there should be a K here. Why did that completely change? Maybe I substituted it in wrong. Okay, so we take this guy and we substitute it in right here. And the way unions work, we can kind of put the union on the outside, and we could say this is just equal to, let's see, it's easier to work with one of them. Let's put the first one in front, big SQ cup from, what do we want? We want I equals 1 to N, and then I have to switch this to J. That should have been a J. Up here it should be J, not I. Let's fix that as well. Okay, and we're just missing that G, so let's put the G back where it was in front of that H. So we have GI. Okay, so we get something like this. We get G expressed as Mn left cosets of K, because, well, we know there are n left cosets for this guy, and we know there are m left cosets for this guy, and because we're multiplying them, there are m times n possible choices. We just have to make sure that each choice is distinct, and then we can conclude what we want, which is this guy. Okay. We know that the index of k in G is equal to n times m if each left coset above is distinct. Okay, so it's essentially what I'm doing here, like how I wrote this as n left cosets of H. If this is m times n left cosets of K, then we have this equation holding. And that's only true if each of these are distinct. Hence, we would have, we know that, yeah, this equals n times m if each left coset above is distinct. So we need to prove that. So we'll suppose we have two elements. We have gi hj k equaling gr hs k, and we essentially want to show that I equals r and j equals s. Okay, so what I'm going to do is, this looks a lot like a theorem we used in the previous problem, which was the criterion for left cosets, which says this. We have essentially this form, and we can get it in this form by using the criterion. So I'm going to invoke that right away. By the criterion for cosets, we have that gi hj inverse times gr hs is in K. Okay, and so we know that this is an element in K. So for some K in K, we can write K equaling essentially this guy. So we can write an element of K as this guy, and now we can manipulate this. Well, we can first do out the inverse. We would get hj inverse gi inverse times g sub r hs, and I'm going to use the imply symbol here. Okay, we have k equaling this guy. If I multiply on the left by hj and hs inverse, we would get hjk hs inverse equaling gi inverse g sub r. Okay, and we have h is an h. K, well, k is defined to be a, let's see, it's a subgroup of h. So k is contained in h as well, and h is also an h. So this entire thing is an h, and it's equal to this. So this guy is an h. So we can say that since hj, k, and hs inverse, let's see, are all in h, we have that g sub I inverse g sub r is in h. Okay, and then once more, I'm going to use the criterion for cosets. Very useful. By the criterion for cosets, we have that GIH is equal to GRH. Okay, but we know that each GI, since each GI is a distinct representative for the H cosets, we have that I is equal to R. Okay, and now if we take which equation? This equation. So we have the equality. So if we take this equation, we have that GI, and now we can say that this is also GI. If we multiply by GI inverse on the left on both sides, we get HJK equaling HSK. And once more, I'm going to use the criterion for cosets on this guy to say that, or actually we don't even need the criterion for cosets. We just use the same logic above. Okay, we get this equality by the same logic above. We have that J is equal to S. J is equal to S. Since each Hj is a distinct representative for the K cosets. Okay, so we have that I equals R and J equals S. So each element here are the exact same. So even if you have two different elements, they're the same element, hence they're distinct. Therefore, each coset GI HJK is distinct, and there are NM of them. Thus, we can just put together what we have, which is essentially this equation. The index of K in G is equal to N times M, which is equal to the index of K in H times the index of K in H. H and G is what I meant to say before. Okay. And we are done with problem number 29.